All right, and with that, I think we can get started. How many of you have heard of quantum computing or have some idea? All right, quite a few people in the room. Okay, so maybe you can help me along the way as this presentation comes along with any questions and stuff. But when most people first hear about quantum computing, they think of it as something that's far off and like a sci-fi movie, futuristic, not here, not now, right? And part of the reason is because everything in the quantum world is so hard to understand. It kind of defies intuition, defies common sense, right? Almost seems mysterious, like how can it work that way, right? Part of the goal of this session today is to demystify that. So how does it really work? I'm going to try and do my best job. So hopefully you'll go away from this session with a more understanding of quantum computing than you started with. And I'm also going to share some resources if you're really interested in taking your knowledge of quantum computing and applying it. There's a lot of resources that I have at the end of the presentation. All right, so with that, let's get started. First up, a little bit about me. I'm a lead software engineer at GM. My day job is building web applications with Java, Spring Framework, and Angular. And something I'm really passionate about and I give a lot of my time to is STEM and STEM education. I've volunteered with Girls Who Code. I'm a Science Olympiad coach at my daughter's middle school, and I'm really, really proud to say that last week I traveled with them to New York, Cornell, for the National Science Olympiad competition. And the most recent organization I volunteered with is Moms Can Code. And again, as the name suggests, it supports moms get into the tech workforce. So they have great programs, and if you all can check it out if that's of interest. You can find me online, Twitter and LinkedIn. I welcome connections. And with that, let's get into what we will be covering in this talk today. A lot of ground. So before I tell you what quantum computing is, I want to tell you why we need quantum computing. Is there really a need for it? So I want to go over that first, and then compare and contrast classical computers with quantum computers, and then get into what quantum computing really is. And the superpowers of quantum computing come from the three miraculous properties, and we're going to kind of talk about those three properties which makes things quantum. Qubits, those are the building blocks of quantum computers. We'll talk about that. The quantum programming model. And it's all not rosy, right? Quantum computing is quite in the infant stage, and there's a lot of challenges and significant challenges. So we're going to cover some of that, the big players. And last but not the least, the programming toolkits that we have available today, learning resources, and how can you get in and take it further. All right. We'll start with quantum computing in the news. So these are some recent headlines from 2019, right? So in Nature magazine, it said, classical and quantum computers are vying for superiority. So this tells you that not only do quantum computers exist, but they are powerful enough that they are vying with our classical computers. And mind you, our classical computers are pretty strong, right? I mean, we've got supercomputers. So we've now got quantum computers that can give our classical computers a run for their money. So that means they're for real. The next headline, GeekWire, Satya Nadella, the CEO of Microsoft, is quoted as saying, mixed reality, AI, and quantum computing will break boundaries for tech. So this again tells you that quantum computing, you've got some big names, big corporations putting in their research, their money, their weight behind it. So it's in the big leagues, definitely. And the last one from New York Times, for a split second, a quantum computer made history go backward. Wait, what's that? That one needs some explaining, right? Okay, so you all heard or seen the movie, The Curious Case of Benjamin Button? Yeah? And I believe it was Brad Pitt who was born an old man and goes into being a young person. How's that possible? Like, we only think of aging as a one-way street, right? Like, you only go age forward in time. It never works backward. But apparently, that's not true. With quantum computers, they were able to take a small simulated, an artificial particle, and turn back time for it just a fraction of a second, right? So it was made possible with a quantum computer. Now, that's not a big deal, right? Like some simulated artificial particle for a fraction of a second went back in time. It's not like any of us are going to get any younger with quantum computers anytime soon. But it's an important statement. Something which we thought was a one-way thing has now been shown that it can go backwards. time is reversible. So that's what with a quantum computer it's possible. So that's some of the latest headlines. I just wanted to give you a lay of the land before I took you back to where it all started. So let's go back in time to when it first started. Anybody recognize this gentleman in the picture? Famous theoretical physicist, Nobel Prize winning. He's Dr. Richard Feynman. And he was one of the first people to imagine that this wonderful, mind-blowing quantum physics can be used to build a new kind of computer. He thought that those powers could be harnessed to build a new kind of quantum computer. He was one of the first. And he would know because he won a Nobel Prize in quantum physics. And this is him dancing away merrily with his wife at the Nobel Ball when he got that prize. So this is in the 1960s. So that's when the idea of quantum computing originated. It's not new. It's been around for a while. So okay, great. We have this new kind of computer that we can build with something called the quantum particles. How different is this new computer from our classical computer, right? Is it like the difference between a new car and an old car? You know, you put a new engine in your old car, a flashy new coat of paint, and it turns into a quantum computer? Not quite, because they're quite different. The difference between the quantum computer and the classical computer is more like the difference between a horse and a hawk. One can run really fast, but the other can fly. You can do things with the hawk. You can go places with the hawk where you can't take your horse. So that's kind of like the difference between the classical and quantum computer. Now you'll ask me, okay, great. You tell me we can build a new kind of computer. It can be powerful. Why do we really need this new kind of computer, right? Well, the classical computer's Achilles heel is where the use cases of a quantum computer lie. So you might think, hey, but our classical computers are so strong, so powerful. We've got supercomputers just like Achilles, right? They can solve most problems. But there are problems where the best of our classical computers fail. They fall short. They don't produce an answer, or if they do produce an answer, it takes so much time to come up with an answer that it's practically useless, right? So that's where a quantum computer steps in. So again, I want to say this again. Quantum computer is not for everything. Our classical computers do a great job, and in most cases, they are just fine for our computing needs. But there's a small niche of problems where a quantum computer can prove its worth. Let's take a look at a couple of these. The first one, modeling natural processes. And natural processes, I'm talking about things like, all right, let's keep going. Natural processes are things like photosynthesis, right? How do plants make food? Or how does the food that we take in react with the elements in our body? How do the drugs that we take in react with elements in our body? Those are all natural processes. Sorry, hopefully somebody will be here to bring this thing back down. So let's take, for example, drug design, right? You got to take a new chemical composition and you have to simulate how it interacts with all the elements in our body under varying conditions, temperature, pressure. There's so many variables, and the big pharma companies have to simulate all this stuff. It takes them millions of dollars and sometimes 5-10 years. If there was a computer powerful enough to simulate that in a meaningful, quick way, then we could reduce the time to market for new drugs. So that's a valuable thing for humanity, and where quantum computers could really be used. The next area, and Dr. Feynman, when it comes back up, I'll show you a quote. He is quoted as saying, and I'll read this quote from here, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And this is what Dr. Feynman is quoted as saying in 1981 at a conference organized by IBM and MIT. So this 1981, way back then, Dr. Feynman could visualize what this quantum computer could be used for. The second set of problems is what's called as optimization problems. You all heard of the traveling salesman problem, maybe, in elementary school, or not elementary, maybe, middle, high school level, or undergrad. So you have a salesman, he's got to visit a whole bunch of cities, And you want to find him the best route. Poor salesman, you don't want him to travel too much, right? And maybe there are some constraints. Now you want to come up with the best solution for this problem. And there's a lot of different routes, and you got to pick the best one. So that's a classic optimization problem. And we have such optimization problems in several areas, right? It could be something personal, like I'm throwing a dinner party and there's a dinner table and I want to put 10 people around it, but maybe John doesn't want to sit next to Jane, and you have all these constraints. So how do you solve for it? Our classical computers can solve this kind of a problem when the number of factors are small, but once it starts to multiply, like these number of factors gets big, the classical computers fail. It is said that if you have 270 things that can flip up and down like switches, the number of possibilities that those 270 switches can be in is equal to like the number of atoms in the universe or something. So that's the number of combinations that you can get with just 270 switches. And sometimes, in some cases, you run into those kind of problems, right? Really, I'm going to take a pause here and see if I can have somebody come help us. Okay.
This happened in the session earlier.
It did? Okay. Thank you.
I think there's just a button back here.
Oh, this one, yeah. Let's see. Wall plate, is it? Oh, yeah. There, it's coming back up. Yay! And hopefully, okay, there you go. All right, this was the optimization problem. Oh. Okay. Oh, replace lamp? All right, we'll keep going. All right. This next use case is probably the most sensational use case, right? Most of the times we want our classical computers to solve problems for us, and we want them to solve quickly. But this is cryptography is one case where we don't want our computers to solve this problem, and we don't ever want them to solve and the problem we're talking about is prime factorization. And that is the backbone of all our modern encryption techniques. We rely on our computers' inability to solve prime factorization, and that's how we can trust our passwords and our secrets with this, because we know that a classical computer can never break the encryption keys, which are based on these really large numbers. So this prime factorization is what's called as a trapdoor function. And like the name suggests, like a trapdoor, it's easy to go through it one way, but it's hard to get back the other way. So if you take two big numbers and you ask, even an elementary school kid can multiply them and come up with the product. But if you have a really big number, one that runs into hundreds of digits, and you give it to somebody or a computer and say, hey, can you figure out the two numbers that I used to get to this number? You can't do that. Classical computers fail at this problem, and that's why it's so hard. But all that changed with this gentleman. His name is Peter Shor. In 1994, he came up with the perfect quantum algorithm for the perfect quantum computer. Now, remember, the quantum computer was not yet in a working condition in 1984, but this gentleman, working at Bell Laboratories at the time, came up with a way that a quantum computer, if it existed, could solve the prime factorization problem. And that just lit the quantum world on fire. Because until then, it was all imaginary. Oh, this new kind of computer, okay, what can it do? But this gentleman showed, if such a computer existed, what can you do? And that kind of scared people, because like, oh my God, is encryption going to go away? But no need to worry, because here's our status quo. In 2012, a 4-qubit, and we'll talk about what a qubit is, quantum computer just was able to factor the number 143. In 2014, it was able to factor 153. But the numbers we use in encryption are hundreds of digits long, and quantum computers are not going to get anywhere close to it anytime soon. But it was an interesting problem, and it kind of helped the quantum computing revolution come a long way. Okay, so great. Who's using it today? These are some real use cases of people using quantum computers. The Roswell Park Cancer Institute using it to optimize radiation therapy for cancer, right? I don't want to go into details, but I just wanted to show that there are real companies applying it to real world problems. Airbus, finding fuel-efficient ascent and descent paths for flights. And the Volkswagen Group, optimizing routes to minimize congestion. Now, we all like that, right? Especially in Atlanta, if we could minimize congestion, yeah, I vote for the quantum computer, yes. All right, so now that we've shown that a quantum computer can be useful, let's kind of get into what it is. Quantum computing, if you had to summarize it, it's anything that exhibits these three properties, right? You can define it. It's any system that exhibits these three properties, and it only happens at a microscopic elementary particle level. You don't see it in the real world. You won't see cars and toys exhibiting these properties, right? It's at that microscopic level. The first one is superposition. So let's get into that first. And I like to go with a simple analogy to explain this. So in our classical world, let's take a bit. You know, we all know that our classical computers are built off of bits, and it has two states, the on and the off state, right? We all get that, like a regular rocker switch, on, off. Well, the quantum world has special property which allows it to not only be in the on and off states, but in a whole bunch of states which are a combination of the on and off states, sort of like the slider switch. So when that slider switch is in the middle, is it on? Is it off? You could argue that it is both on and off. It's 50% on, it's 50% off, right? So that's the way to think about this superposition property that the quantum particles possess. There are two states, two basis states, but they are not restricted to remain in those two basis states. They can exist in any combination of states in between, and that's just the nature of those fundamental particles. And that's what gives them, it's kind of like the secret sauce, the secret superpower of quantum things. So, okay, great. So you tell me that a elementary particle can exist in all these states in between. How exactly do you build it? Well, companies have tried to build this in several different ways. So one of them is by using the polarization of a proton. So apparently from physics, if you all remember, you know, it says that the polarization of a proton, think of it like a wave, and it can be vertical or horizontal. But at that time, we only learn of those two states, but in reality, it can exist in a combination. The polarization is a combination function that could go between vertical and horizontal. And likewise, the spin of an electron can be used to simulate a quantum system, up, down, and everything in between. Superconducting wires, where the direction of the wire current goes left, right, or it kind of can be in between. So the point is here, you can take certain special elementary particles and use their property, which is that they can exist in a combination of states. How is this going to help us build a new kind of computer? We'll get into that. But before, so okay, you tell me that it can exist in a superposition of states. Can I see it? No, the quantum computer doesn't, the quantum world doesn't let us, observers, view its superposition state. So when you actually go to observe the quantum particle, it goes into one of the two base states. So when you observe it, you'll either find it in 0 or 1. You can never find it, you can never observe it in that superposition state. That's just a fundamental law of physics, right? So what then gives the quantum computer its power? So let's imagine you have one qubit, which can exist in 0 or 1 or all states in between, and you have another qubit, which can also exist in a 0 state, a 1 state, or all the states in between. Now, in a regular world, in our classical world, when you look at those two qubits, you'll either find it in 0, 0, 1, 1, 1, 0, or 0, 1, right? Only one of those states you can find those two bits in our classical world. But because of this superposition property in a quantum world, you can actually, there is a certain probability of these qubits being in one of any 4 states. So you can get one of those 4 answers with a certain probability. Maybe 50% of the time you get answer 1, maybe 20% of the time you get answer 2, and 10% answer 3, and another 10% answer 4. The point is, you can get one of 4 answers. In the classical world, you could only get 1 answer. But in a quantum world, because of this superposition, you can get 4 answers at one time with 2 qubits. And if you keep adding these qubits, the number of answers that you can get, the number of things it can work with increases exponentially. And that is the source, the secret of the quantum computer's power, the superposition. So just to get a visual on this awesome power, right? On top, I've got the supercomputer, the world's fastest supercomputer. That's the IBM Summit computer, which is, I think, deployed in one of the US government facilities. It's the world's fastest computer. And if I told you, can you double the capacity of the supercomputer? Guess what? You'll have to get another big room, which is like, I think each room is like 2 tennis courts. Get another room, assemble the whole supercomputer again, and that's how you double the capacity of a supercomputer. For a quantum computer, guess what you got to do? Add just one more qubit, and that effectively doubles the capacity because of that exponential increase of power. So once you get them right, it's easy to make them really powerful. But we have to still get them right though. All right, so just a mathematical representation of these qubits, and I'm going to go through it a little faster because we lost a little bit of time. So we said that a superposition state can exist in any possible combination of the 0 state and the 1 state. You can kind of think of it as the Earth, the North and South Pole being the 2 states. Then any point on this Earth is a possible superposition state. Now, how do you define that superposition state? Now, if you take any point on Earth, the way you do it is, relatively with latitudes and longitudes, right? You say that this is 30 degrees north of the South Pole. You kind of define the position of any point on Earth relative to the North and South Pole. It's the same concept with this qubit. If you imagine all the superposition states as the sphere, which by the way is called a Bloch sphere, the position of any one state you can define in terms of the 0 state and the 1 state, which are the basis states. So again, going back to the slider switch example, let's say the switch was 80% on, 20% off, right? Like let's say it was closer to on than off. You can say it's 80% on and 20% off, similar to that. So these numbers, which tell us the relative position, are called the amplitudes. And the complexity, this is where it kind of gets a little complex, and I need you to take a leap of faith with me. So these numbers, unlike probabilities are like positive numbers. These numbers can be real and imaginary, and they have a magnitude and phase associated with them. So that's the challenge, right? But that's what gives them their power. So you can think of it as a wave. You know how in physics, when you think of light, you have the wave-particle duality, you have the light exhibiting wave-like properties. So you can think of these quantum states as exhibiting those wave-like properties. And go with that wave reference a little bit with me, and because that kind of goes into the second superpower. So when you have 2 qubits, and you have all these superposition states, right, and think of them as waves, we know from our classical world that when waves interact, they can interact in phase or out of phase. And when the waves interact in phase, the 2 waves kind of make a bigger wave. And when the waves interact out of phase, they kind of kill each other. So that's kind of what happens when you take 2 quantum systems, 2 qubits, and their superpositions, you kind of put them together. They interact, either reinforcing each other or canceling each other out. So kind of like the noise canceling headphones. And we want to program our quantum computer in a way that the correct answers have constructive interference and they get amplified, because when you measure, you want the probability of the correct answer to come out at the other end to be high. Because remember, when you measure, you cannot see the superposition states. You can only see the 0 or 1. So you want to increase the probability. Let's say 0 was the correct answer. You want to increase the probability that it will be a 0, and that's through this constructive interference. And likewise, you want the wrong answers to kind of destructively interfere and die out, right? And the last kind of quantum property is called entanglement. And this is where, so in the interference, kind of like the 2 superposition wave-like things came together and either amplified each other or canceled each other out. This is a special case where they come together and they kind of lock in, right? The superposition states of the 2 qubits kind of lock in. And once they lock in, even if you take them apart millions of miles and put them at opposite ends of the Earth, they somehow still remain connected. Kind of like, hey, my wavelength matches with yours. Their wavelengths match or something, I don't know. So they stay connected, the point is, and once you make a measurement on one of those entangled qubits, the other one will decay into a classical state in a predictable manner. So that's what is entanglement. And Einstein called it spooky action at a distance, because you entangle these qubits, take them apart, you measure one, and somehow magically the other one knows that this guy here has been measured, and it goes into a corresponding superposition state. So that's kind of how the quantum world works: superposition, interference, entanglement. Those are what give the quantum its superpowers. So a little bit of a compare and contrast with the classical and quantum computer. In a classical computer, we are used to predictable outcomes, right? When you give a classical computer 2 plus 2, you know the answer is 4, and it is always 4 no matter how many times you repeat the operation. But because of the probabilistic nature of quantum computing, you'll never get a predictable answer. You'll get a probabilistic answer. So you ask a quantum computer what's 2 plus 2, it says, oh, 99% of the time it's going to be 4. And that's good enough. For the big problems that we solve, a good guess is good enough, right? Because these are problems you're not able to solve with a classical computer. So again, a classical computer is built with bits, whereas a quantum computer is built with qubits. Bits, are like your on-off switches, whereas the qubits are like your slider switches. In the real world, we implement on-off switches with tiny transistors, whereas in the slider switch, the qubits, we looked at protons and electrons and trapped ions. That's how you implement them. And now, in order to program our classical computers, we use gates, right? Like the NAND gate, NOR gate. If you do the basic logic theory class, you have all these gates. And we have a similar programming model for the quantum computer, which we'll take a look at next. Actually, this part is kind of very intuitive and easy, because if you're familiar with the programming model for a classical computer, the quantum gate model follows the classical computing model. There's another kind of quantum computing model which we'll not get into. It's called quantum annealing, and there's a company which is doing that, but we'll not get into that. We'll look at the quantum gate model, which is much more like our classical computing model. So you start with the qubit, which is the basic building block. Then you have operations, quantum operations that you can perform on the qubit, which transforms the qubit state. Then you have quantum gates, much like our logic gates, which implement the various quantum operations. And then finally, you take these gates and you kind of put them together in a circuit to build an ordered sequence of gates that does a certain thing and gives you your output, right? And these quantum operations, they're different kinds. You have the unary operations, which operate on a single qubit. Like, for example, hey, negate the qubit, right? Like, take it from a 0 state to a 1 state. That's a unary. You've got binary operations, which act on 2 qubits, and we'll look at some examples of these. We've got reversible operations, which is where I'll tell you what the operation is, and I'll tell you the output. Can you tell me what the input is? If you can, that's a reversible operation. So for example, let's say the operation is not, right? Flip it. And I tell you the output is a 1. What's the input? We all know it's a 0 because it's a not operation. You got a 1, so the input had to be a 0. But there are certain operations where if I tell you the operation and the output, you cannot tell what the input is. And an example is an operation which always turns the bit into 1. No matter if the input is a 0 or 1, you get an output of 1. So that's a non-reversible operation, right? Because it always takes the output to 1, no matter if the input was 0 or 1. In quantum computing, we mostly use reversible operations because it's easier to implement those. So these are some of the gates commonly used in a quantum programming model. So in the classical world, a NOT operation was simple, right? 1 to 0, 0 to 1. In a quantum world, it gets a little more complicated because a qubit can have a magnitude and a phase. You may only want to flip the magnitude, like a +3 to a -3, or you may want to flip the phase, which is a direction flip. Think of the sphere again, right? You're flipping either the magnitude or the direction or both. So depending on what you're flipping, you have these different operators. Then you have something called a conditional NOT operator, which is the C NOT. And this is a 2-input, 2-output operation. You have, let's say your input is, one is a control input, one is a target input. If your control input is a 1, you flip it. If it is a 0, you don't flip it. So your control bit is kind of influencing what happens to your target bit. So that's a controlled NOT. You have a control not, which is called a Tivoli gate, which is usually identified by the T. Here you have 2 control bits and 1 target bit. So if the 2 control bits are in a certain value, then flip the target bit, otherwise don't do anything to it. Then probably the most important quantum gate is the Hadamard gate. That's what it's called. And what it does is it takes a qubit from a classical state of a 0 or a 1 and puts it into a superposition state. The superposition, and it puts it into a equal superposition. What that means is it takes the qubit into a state where there's 50% chance it goes into a 0 or a 50% chance it goes into a 1. That's called an equal superposition, right? So again, when you measure a qubit, you can only see it in a 1 or a 0. You cannot see it in any of the superposition states. But you can always tell the probability. When those probabilities are the same, that means it's an equal superposition. And that's what the Hadamard gate does for you. And lastly, you've got measurement gates. And this is where you're actually measuring your quantum qubit, and it collapses into either a 0 or 1. Right? So these are some of the common gates that you would build your quantum circuits with. So let's look at kind of example of a quantum circuit. So this is from an IBM circuit builder. So they've got all these tools that they've made available, and I've got links for all that at the end of the presentation, and I believe the presentation is going to be shared, so you'll get all those links to those resources. But this is something that you all can play with, go out there and play with. So this was built with an IBM circuit composer. So what you see on the top, Q0 is qubit, the first qubit. The Q1 is the second qubit, and time is going from left to right, like, you know, we are used to. And the X is saying that, okay, flip the first qubit, then the plus operator is saying, you know, use the top bit as the control bit and use the bottom bit as the target bit and do a control not operation, and then put them in superposition and so on. So you kind of read that in a sequential manner, and you can drag and drop those gates and build those quantum operations. And the bottom line is your measurement gate, what the qubit eventually collapses into. So when you apply the measurement gate, you see that the qubit collapses to a 0 or a 1. So this is how a quantum circuit looks. And this is how you can build it with the quantum gates. All right, so that's kind of like a quick tour of the quantum programming model. I now want to shift gears and show you like who are the companies in this space and what they're kind of doing. You'll find all the big names out there, right? Google's saying that it can achieve quantum supremacy in 2019. So this may be a milestone year. They've got a quantum chip. They call it bristlecone. And it's got 72 qubits. That's a lot of qubits, actually. It may seem like a small number, but in qubit world, in quantum world, 72 is a big number. So Google thinks that with that 72 qubit chip, it can prove that the quantum computer can do something better than a classical computer. So we have to wait and watch. Maybe in the second half of this year, that announcement might come, right? That'll be great. IBM, in the beginning of this year at the Consumer Electronics Show, CES, they unveiled their Q System 1, which is their first quantum system, quantum computer that they've made available to the public. And anybody, they've made it accessible via the cloud. So we can all go out there and start playing with it using their open toolkits. You've got Chinese Alibaba, Chinese government, European Union, billions of dollars they have given to quantum computing research. I mean, that's serious money. And NASA and NSA are putting in lots of money. So and D-Wave, that was the company, the one that you see in the corner there. That's the startup that's using that other kind of programming model, the quantum annealing model. They are pioneers in that area. And they've got that quantum computer built. And in fact, it was their quantum computer that was used by the cancer use case that I presented before. It was done on the D-Wave quantum computer. Rigetti, they believe they can deliver on a 128 qubit quantum computer soon. So there's lots of companies putting in a lot of research in this area trying to build better quantum computers. What do they look like? Like a mad scientist project, right? All these wires jumbled up and going in, and you might wonder, why do we need the quantum computer? After all, it's like an elementary particle this big. Why do you need all this for it? Well, It's because you got to keep this quantum computer isolated. It needs to kind of be in its own shell. It can very easily disintegrate. That's the reason. This is actually a huge refrigerator. It keeps the quantum computer really, really cold so it doesn't get all the thermal interactions and everything else from outside. But don't judge them too harshly, because throwback time, remember how the classical computers made their start, right? A room full of computer, and now you've got a computer on your watch in about, I don't know, 60 years. That's how small the footprint got. So just have to give them a chance. So it is said that 300 perfectly entangled qubits in superposition would have so much capacity that it could map all the information in the universe starting from the Big Bang, right? That's the power. So what are we waiting for then? Well, not so fast, because there's some serious challenges, and I kind of talked to that a little bit before. So the quantum system exists, these qubits, they exist in that special quantum state for like fractions of a second, sometimes just milliseconds. And you can make them do work for you in that short amount of time, but it is very easy for them to tumble out of that quantum state and into the classical state, right? Anything from heat, the vibration of the Earth's magnetic field, atmospheric pressure, all these things interact with that quantum system and can make it come out of the quantum state, and there you've lost it. So the big challenge, and that's called decoherence, when a quantum system loses its quantum state and becomes a regular classical boring bit, that's called like a decoherence, right? And all these companies, the big players, they're trying to figure out how can we keep these quantum systems in their quantum state longer so we can get them to do some useful work. Now the way, and this decoherence leads to errors, right? Once a quantum system kind of tumbles out, it starts, the wrong answers. You remember how we said we want the right answers to get amplified and the wrong answers to kind of die out? Once it gets out of its quantum state, the wrong answers start to, grow bigger and errors creep in. The way you deal with it in a classical computer is, let's say you've got 32 bits, you throw in some error correction bits, right? And those error correction bits compensate for any errors in the model. In the quantum computer, you need a lot of error correction bits. That's the challenge. You need sometimes thousands of physical qubits to make a good quality, logical, error-free quantum computing bit. And we are nowhere there yet. So that's the big challenge. How do you manage the noise? How do you reduce the errors? How do you keep the quantum system in a quantum state long enough that it can do something useful? And there's, of course, engineering challenges, right? Like you want to make it smaller. The way the quantum computer is right now, you can't put it on your Christmas wish list anytime soon. So it's always going to be in one of those big, rooms and somewhere which you can access on the cloud. So those are some of the engineering challenges. And the cost, of course. So that's what are some of the big challenges that some of our big companies are dealing with right now. So there's a lot of debate about it, right? I mean, you can read up, there's this very famous article, it presents a case against quantum computing, like why this is a piper's dream, right? Why it cannot be realistically achieved. And of course, there's the rebuttal, the case against the quantum computing. And if you go look up these forums, there's researchers and physicists on both sides arguing that, no, we can do it, we can do it. So we're still kind of like in the debate stage. It's not proven yet. But we do have systems that work for small problems. But to realize the full potential of quantum computing, there's still a lot of ground to cover before we can get there. All right. So now I want to get into, okay, great. You've sold me on quantum computing. There are people doing real work in it. How do I get started? What are some of the resources out there? And good for you, if you really are interested, there's a ton of resources. And actually, there are research firms which are saying that there's going to be a skills gap in this area. So they're going to need people. They're going to need to train a lot of people in this area to, work with these quantum computers. When they finally come into being, you need people to work with it, right? So here are some resources. Brilliant is a company, and Microsoft and Alphabet, that's Google's parent company, they have collaborated to bring this course. It's kind of like, your Pluralsight, or think of it as those learning platforms. They have a special thread all on quantum computing, takes you from the beginning to the advanced concepts, how to build circuits, all that in there. Google has open source frameworks called Google Circ. It's a Python framework, but they've got lots of easy to get started Jupyter notebooks. And there's Google Open Fermion that's more specialized towards chemical applications like biochemistry. Again, we want to use quantum computing for those hard to solve problems, right? So they're niche problems. So this one is catered towards your chemistry kind of problems. IBM has a wonderful website. The circuit that I showed before was the Circuit Composer from IBM. You've got that's also a Python framework, and you can use that. This is that Circuit Composer I was talking about earlier. You've got all those gates up top and these qubits, and they have neat little guides which tell you, okay, if you wanted to do a simple program, here's how to do it. I believe there's a Medium article published where somebody used a quantum computer to simulate some kind of battleship game. So any gamers out there can go check out that article, and that even gives you like, okay, this is the battleship, and here's how you simulate it on a quantum world, and you can submit your program so it can be run on the cloud using these online APIs. Microsoft has got stuff. They call it the quantum katas. It's all on the GitHub. They have a Q#. They have a new programming language that they call Q#, kind of like C#. Those folks familiar with C# might want to work with the Microsoft toolkit. Again, Rigetti, they've got their own SDK. I mean, there's no shortage of toolkits and APIs out there because there's all the companies, they want you to come to their quantum system. They've all made toolkits and APIs available for you to play with. Now for some light side, if you want a comic on quantum computing, definitely check this out. It's called The Talk. It's hilarious. I actually wanted to kind of go through the whole thing, but it was like too long. I'm like, this is entertaining, but I'm just going to put a link out there. So if there's one thing that you're going to check this one out. It's really cool. Sleeping and cute sleeping puppies are always a winner. So there's some light side for you guys. And with that, we reach the end. Thank you all for coming to the session.